तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the IV characteristics of the Schottky barrier diode, okay, and we have shown that it is similar to the p-n junction, except I naught is different. We have gone into details of that, why I naught is different. Okay. And to just say in few words, the difference is actually here. The electrons which are reaching the surface with the velocity, mean velocity, are n of s, which are smaller than the carrier concentration in the bulk. Now, once they cross this, once they come in thermal equilibrium with the metal electrons, they are very small quantity compared to this total number of electrons. So, they can be taken away, same current can be transported with a very small velocity, because it is J is equal to q n into V. Here n is small, but V is large. Here n is very large. So, with very small v, the same current has been transported. So, what we are telling is, in this type of device, the transport of carriers here is by drift. There are no charge storage effects. Okay. There are no charge storage effects. We come back to that thing. There are no charge storage effects here. Yeah. Okay. So, I will just go through this once. Referring to that diagram there, what we saw just now, we have seen that the current transport is only due to electrons. Electrons are transported from the semiconductor to the metal, and they are taken away by drift. There is no chance for the charges to get accumulated in the metal, because they are very small quantity compared to what is available in the metal. What is 10 to the power 22 or 23 per centimeter cubed in metal, compared to that, these injected carriers are very, very small. Charge storage effects are not there at all, and they are not collected there because they are removed immediately. So, that is why what we say is it is a majority carrier device. The current transport in the semiconductor, in the n type semiconductor, is by the majority electrons, and in the metal, of course, it is again electrons. So, there are no minority carrier storage effects. We will verify this later with some more details, but it holds good even when we analyze, we will see it. Other aspect that I want to mention here is, these are also sometimes called Schottky barrier, majority carrier device. Of course, that is a general term. It is also called as a hot carrier device. So, when you want to see, that is why I just put this diagram here. The hot carrier device is called hot carrier because the electrons which are crossing this barrier, having the energy more than this barrier, when they are just at the boundary, the energy of these electrons is above that of the electrons in the metal. So, this is the energy distribution of the metals, right, slightly above the barrier. These are even above that, because those are the ones which are giving rise to current. So, these electrons have energies more than the electrons in the metal which are in thermal equilibrium. So, usually when you talk of an electron, it is in thermal equilibrium with the lattice. So, these electrons which belong to the metal, they are in thermal equilibrium with the metal, whereas these electrons just immediately after they are injected, they are not in equilibrium. That means, their energies are more than those of electrons which belong to the metal. Usually, the electron exchanges energy with the lattice, and it is in equilibrium with the energy of the lattice, that is the room temperature. So, energy corresponding to these electrons is the room temperature or whatever is the temperature of the metal, whereas this is higher than that. that means it looks as if the temperature of those electrons is more than the room temperature. That is why it is called as hot electron. It is hot compared to the electrons which are in thermal equilibrium with the metal. Why we are telling that is, the same electrons here can occupy higher energy levels if you heat up the metal. So, here without heating they are at higher energy, because they are just belong to this metal and cross the barrier. So, that is why these electrons are called the hot electrons, okay? And they are not in thermal equilibrium with the metal just at the instant of injection. Now, it will immediately collide with the lattice within picoseconds time, okay? It will come in thermal equilibrium with the metal. So, its identity is lost, it is no longer hot, because its energy is lost to the lattice, it is in equilibrium with the lattice. So, it is hot electron for a short while. So, this device is called as hot electron device for that, from that point of view. Nothing hot about that, except that it is hot electron for a short while. Now, there are also, we have seen, just now we have discussed, there are charge storage effects are minimum. I am using the word cautiously. Actually, charge storage effects are absent almost totally. Okay. Now, they are minimum. All right. So, also because the charge storage effects are minimum, the devices can switch very fast. Okay. See, the switching speed of a diode is larger if there are stored charges. When there are stored charges, it behaves more like a huge capacitor, lot of charge is stored. Okay. Then to turn off the device, you must remove the charge completely. Okay. So, that takes time. From the on state to off state, if it has to go, the charges will have to be removed. So, the delay times are involved. That is why the p-n junction diodes are slower, because of charge storage effects. In the p-n junction devices, to make it faster, what you do is you actually kill the lifetime, reduce the lifetime, so that stored charges for a given current is less, because current is stored charge divided by lifetime. So, okay, if the lifetime is smaller, you can have a smaller Q, so that Q by tau is same. In p-n junction, current I we can say as stored charge divided by lifetime. I can reduce the lifetime, I can still have the same current with smaller charge. Okay. So, that is the implication of that. So, I will not go into details at this moment, maybe when we discuss logic circuits I will come back to this. So, this will be smaller if lifetime is smaller. So, you actually deliberately reduce the lifetime of carriers by certain methods like gold doping, etc. So, to make p-n junctions faster, you must have lifetime control techniques, but here there is no stored charge, automatically it is minimum, it is a majority carrier device. So, that is why these devices, Schottky barrier diodes, are faster, basically fast devices. So, in gallium arsenide based logic circuits, you will use quite a bit of these Schottky barrier diodes for some level shifting, etc. Now, it goes without telling, all these things together makes that device, Schottky barrier device or diode, or the devices based on Schottky barrier, very effective in high speed digital circuits. Okay. Now, quickly run through what we have been talking. Ideal characteristics of a diode. Now, we will just see, are these characteristics exactly same as we have been talking. So, what we said is the reverse bias voltage minus V r, when you apply, the current reaches a constant. That is one of the characteristics that we said. And also, and that is of course, when the reverse bias voltage is at least about 100 millivolts, when you apply, see, after all it goes from 0, it keeps on increasing, it saturates at I naught by the time about 100 millivolts, that is 4 V t. Forward bias, we said it is I is equal to I naught e to power v by v t minus 1. I removed that minus 1 there, because that becomes small compared to e to power v by v t. So, about 100 millivolts 4 V t. Now, if you plot log I versus V, log to the base 10 of current versus voltage, it will be linear plot, because exponential on log scale becomes linear. Okay. And the slope of that will be 60 millivolts per decade. We will see that immediately what happens further. Reverse bias, now non-idealities. It really strictly does not follow this rule. In some cases you have got, or in most of the cases, reverse bias current does not saturate at I naught. Okay. It keeps on increasing. And the forward bias IV characteristics cannot be expressed as I naught e to the power of V by V t minus 1. There will be a factor n coming in the sense it does not increase as steeply as you expect, it increases slightly slowly. So, that is I naught s, okay, whereas this term n will be slightly more than 1, which you call it as ideality factor. You call it ideality factor because that is the one which tells you how much it is deviating from ideality. Sometimes people confuse and say it is non-ideality. It is actually ideality factor, saying how much it deviates from ideality. If n is 1, it is ideal, n is deviating from 1, it is non-ideal. So, n always is greater than 1. Okay. Now, to plot on a log scale what we said, ideal characteristics is that one. I log to the base 10 versus V volts will be I naught e to the power of V by V t will be linear. Now, if the characteristic is in this form, that is I naught e to the power of V by n V t, logarithm of I is equal to, that is what I am putting here, okay, logarithm of I to the base 10, remember, is equal to logarithm of I naught to the base 10 plus V by V t, V by n V t. Since we are taking log to the base 10, you will have this factor log 10. All this to the base 10, this becomes base to the e. So, what we have now is an equation which is linear, okay, and the slope of that, please remember this is log scale. So, we will take the slope in the log scale itself. So, what we are trying to see is, I just put it deliberately because there is some misconception in this here many times. So, you write it as logarithm. Now, you to find the slope in this log semi log scale, what you do is delta V, differentiate this with respect to the whole term itself. So, delta V divided by delta of logarithm of base 10 I. So, this when you do that, this term goes off because it is a constant delta, it does not vary with voltage. Okay. So, this particular quantity now becomes V by n V t. Okay. What I have done is I have taken this log to that side and delta V by delta log I, that becomes equal to this quantity, just rearranging the things, n V t into log 10. This is a very well known thing to everybody, but I just put it in the form of equation. So, n is equal to 1 ideal case, delta V by d log I will be equal to V t log 10. V t log 10, V t is if I take about 25.6 or so, this turns out to be 60 millivolts. So, if n is equal to 1, it is 60 millivolts. So, n is equal to 1, it is 60 millivolts slope, that is a current will change by 1 decade. When I say this is 1, it changes by 1 decade for a change in voltage equal to 60 millivolts. So, the implication of that is, if I change the voltage by 60 millivolts, the current will change by 1 decade. Okay. Now, if ideality factor is 1, if n is more than 1, let us say it is 2, the slope will be, if n is equal to 2, that will become 120 millivolts, 120 millivolts per decade. Meaning, if this is giving 1 decade current change with 60 millivolts, this current will give 1 decade change with 120 millivolts, that way it is less steep. Current increases slower compared to the ideal characteristic. So, these are the things people have observed. On a log scale it is like this, on a linear scale that is how it is. The actual thing what happens is, the device characteristics this curve is ideal. I naught is saturating, and in non-ideal case it does not saturate, it keeps on increasing. So, we will see what are the causes of that, and in the forward case just now we saw the current increases less deeply compared to the ideal case. So, it is slightly shifted to the right I put. Actually, it will go still exponential, this is exponential, but less steeper. Okay. Instead of e to the power of v by v t, it is e to the power of v by n v t. Okay. So, that is the practical situation, this is ideal. I just put this diagram back what you had seen earlier to see what are we missing out here. Okay. We took into account in the current transport of only of this term, that is the electrons which are able to cross the barrier, that is the thermionic emission current as far as this side is concerned. Now, there are other currents which we have not taken into account. We will examine and see whether we really should worry about those. Okay. So, what are the other currents? One of them is this current, that is the hole injection and recombination in the neutral region. Okay. If that is present, it is a dangerous situation. If there is hole injection, if the current is controlled by hole injection, that means there are stored charges, minority carriers in that region. So, you can easily say that that will be negligible, okay. But you can compare and see what will be that current by comparing to the p-n junction model. Okay. The other current is the generation recombination current within the depletion layer, recombination in the case of forward bias, generation in reverse bias. There is one more current component which actually is the tunneling current. As you go up in this region, the barrier width, for example, if I take it here, it is large. If I go up here, the barrier width is very small. So, once the barrier width is very small, the electrons which are present in that energy can just tunnel through that. That is called quantum mechanical tunneling. That is, it becomes probability of finding the electrons here as well as here becomes same almost. So, you can find it either here or there. That is the implication of that quantum mechanical tunneling. Otherwise, you can say there is a very thin layer, it can just go through that. That is very simple physical explanation. Okay. So, these are the three. There are other additional things which we have to worry about. So, possible causes I have summed up: hole injection, what I mentioned just now, recombination generation in the depletion layer. There is one more term which I added here, which is not shown in the diagram, that is image force lowering of barrier. In the sense, go back to the previous thing, the barrier here is this quantity from top to this edge. That barrier gets lowered due to a phenomena called as image force lowering. We will see that. In fact, if you see, open up Zay's book, right on the first page on the Schottky barrier, what is talked about is the image force lowering, which lowers your barrier immediately. In the sense, it becomes slightly difficult at that instance. So, I brought it out later. After understanding what is the barrier, okay, we can talk of this barrier height reduction, that barrier reduction due to the image force lowering. Now, that is the third one, we will examine that. Fourth one is quantum mechanical tunneling, which we have just now mentioned at the top. Other one is insulating interfacial layer, always will be there, that will affect to some extent. We have already taken into account that while discussing the IV characteristics or the phi Bn determination. Okay. First, we will take the hole injection current in the Schottky barrier diode. Should we worry about that? What I have drawn here is not the energy band diagram. I have drawn the carrier concentration in the semiconductor. Up to this point, it is majority carrier thermal equilibrium, and this is the depletion layer. WD is the depletion layer width. So, when you get into depletion layer width, the carrier concentration dips. You remember, we have estimated this quantity n of s, and n of s is equal to n n 0 into e to the power of phi by v t, where phi is negative in this case. So, that quantity is smaller. So, I just plotted the whole thing here. Correspondingly, the whole concentration goes up here. If you take a p-n junction, you will see in the p-n junction, I am just putting the model exactly same as p-n junction without getting into too much complications. Okay? In fact, people have shown that with this simple model. Hole concentration will be changing like that, it will go up. When the depletion rate goes up a little bit, okay? It is still small quantity. So, just at the boundary, you will have hole concentration raised to p-n 0, like in the p-n junction. When you forward bias a p-n junction, the hole concentration at the depletion layer boundary goes up from p-n 0, from this value slightly up, p-n 0 within the bracket at x equal to 0, x naught. And the value of hole concentration here from the simple p-n junction theory can still be written, whatever is the voltage appearing across the depletion layer, it is by that quantity that it goes up. That is the law of the junction. Same law we are using here. So, applying p plus n junction theory, p-n 0, that concentration is p-n 0 e to the power of v by v t. Now, you may ask, why have you not changed it here? That also will go up, but the change here is very small compared to majority carrier. So, it is almost flat. It is like this may be 10 to the power 15 concentration, this will be 10 to the power 12. So, 10 to the power 15 plus 10 to the power 12 is 10 to the power 15. So, just we keep it there. Okay, you are not showing the change here. In p-n junction, you see that change in increase in the majority carrier if there is high injection level conditions, which usually we discuss in power devices where high currents are there, otherwise it is not there. So, you have got that now, p-n 0 raised by that amount. What will be the current transport due to holes here? Now, you saw there is current transport of electrons from here to that due to the barrier. Now, if there is concentration gradient like this, okay, if you have concentration gradient, current transport due to the holes will be by diffusion. So, if you want to find out what is the hole current, you just all that you have to do is find out that. This is straightforward, just like in the case of a p-n junction. See, for example, J p is minus q dp dp by dfs, because the current is by diffusion, there is no field there, and that is q dp p-n 0 minus p-n 0 by L p, standard p-n junction equation. They are making use of the whole current injected in the case of p plus n junction for estimating this. Exactly same, I do not have to spend too much time on this. And this p-n 0 is p-n bar 0 e to the power v by v t. I just substituted for this, this equation becomes like this. Okay? All that I have done is made use of the expression for p-n 0 into in terms of thermal equilibrium value into e to the power v by v t. So, what is this quantity? That quantity is J naught of the p plus n junction, okay? This quantity. So, it is J naught into of the p plus n junction, please be careful, this is different from that of the J naught in the Schottky barrier diode, because that mechanism is different. We have spent enough time discussing that. So, that is that quantity. Now, let us see, compared to the J n, what we estimated as the Schottky barrier diode current, totally due to electron current, that is J naught. I am using T e here to distinguish from this J naught. There are two J naughts now, one J naught belonging to the whole injection, which is p plus n junction, other J naught due to the thermionic emission, and this is the Schottky barrier diode. So, what you have to find out is how much is the ratio of this and this. So, when you divide J n by J p, which actually you can call it as injection ratio, the e to the power v by v t gets cancelled. So, the ratio is actually equal to J naught thermionic emission by J naught p plus n. Okay. How much is that? J naught p plus n is how much? For silicon, we saw it is something like 10 to the power minus 11, 10 to the power minus 12, and J naught thermionic emission is something like 10 to the power minus 7. We estimated that. So, this term is much larger. If you go back to our previous discussion, this we said in silicon it is about 10 to the power minus 7, and this is about 10 to the power minus 12. In the case of gallium arsenide, this is much, even much smaller than that here compared to this. This is 10 to the power minus 9, this may be 10 to the power minus 17 or minus 18. So, this term is 10 to the power 4 to 10 to the power 5. What you are telling is this current, electron current, is much larger compared to hole current. So, what you are thinking, that is, could this hole current injection be leading to non-ideality? Will not hold good. You do not have to worry about this at all, the denominator term. That means, you do not have to worry about J p compared to J n. So, J p is negligibly small. So, we have eliminated that. Let us go now into the generation recombination current, second one that we are telling. We are taking a look at each of those terms. So, generation current, you are familiar about that in the case of p-n junction, which is actually given by, it is important in reverse bias condition mainly, okay, and comparatively also when the forward current is very small in p-n junctions. We have seen that. So, for a p-n junction theory, this generation current is actually equal to some constant J g r naught e to the power v by 2 v t minus 1. I am not getting into deriving this, we will just use it. Okay. Generation current, because this in p-n junction theory we have discussed it in many occasions, or some other courses it has been discussed. So, but you can take it. All that we are trying to see is, should we be worrying about this particular component in the case of Schottky barrier. So, this is the generation recombination current, when this constant term is actually q n I into W d by tau, where n I is the carriers generated due to covalent bond breaking. That is why I put it as the intrinsic concentration. So, this n I is proportional to e to the power minus e g by 2 k t. Okay. W d is the depletion layer width, tau is the space charge layer lifetime, because what we are talking of is what is happening within the depletion layer. Okay. Let us compute these values. J g r naught, that is what we are talking of is, first let us evaluate that constant, and once we evaluate that constant, then we can find out. Rest is the varying with voltage. Gallium arsenide, let us see. In gallium arsenide, N I is something like 10 to the power 6 per centimeter cube, and built-in potential is almost 1 volt, 0.9 volts, 1 volt. I am just putting 1 volt for simplification, close to that at least. Very easily, 1.43 is the band gap. So, 1 volt barrier built-in potential you can easily get. All that you have to ensure is, you do not say that built-in potential is more than the band gap. Okay. So, they will be caught there. If you say silicon has a built-in potential of 1.2 volts, then that is not correct. So, it is always less than the band gap. W d for doping of about 10 to the power 16 is about 0.3 microns, rough number. Tau 0.1 microseconds. I have taken 0.1 microseconds because gallium arsenide, it is a direct band gap semiconductor, very easily carriers can recombine, just one transition. All that you have to do is the energy conservation, there is no need of momentum conservation. So, the lifetimes in gallium arsenide are small. So, this term J g r naught, I am substituting Q 1.6 into 10 to the power minus 9, N I 10 to the power 6, depletion layer width 3 into 10 to the power minus 5 centimeter, that is 0.3 microns, divided by lifetime 0.1 microsecond, 10 to the power minus 7, the whole thing turns out to be 4.8 10 to the power minus 11. Now, what we have to be concerned is, how does it compare with J naught of the thermionic emission? Now, you have to recall the numbers that we have worked out in our previous discussion. We have worked out and seen for gallium arsenide that J naught thermionic emission is about 10 to the power minus. In fact, at that number we worked out 1.24 into 10 to the power minus 9 amperes per centimeter square. I just put approximately 10 to the power minus 9 because we are considering about only that. Now, this quantity is minus 11, definitely smaller than that. So, actually you may not have to worry at around 0 bias, but when you go on increasing the depletion layer width, what would happen? In the reverse bias condition, this quantity keeps on increasing, the width of the depletion layer. Supposing the width of depletion layer goes up from 0.3 micron to 3 micron, 10 times more. This can become 10 times more. That is 4.8 into 10 to the power minus 10. Still, it is not bad. It will not affect so much. That is what we are telling. Okay. Forward bias. How will it affect in the forward bias condition? If you recall the diagrams that we have been plotting, V and I, log is 10 if I plot. Thermionic emission current J I naught, or let me put it as J itself, so that we can always put J or I, it does not matter, multiply by area you get current. So, that is that quantity, that is that quantity that we are putting here is J naught thermionic emission. The value of that is about 10 to the power minus 9, and it goes up on the log scale linearly. I am putting the case where it is e to the power v by v t. So, this is n is equal to 1. You would have got ideal characteristic like that. Now, we are trying to see whether this term generation recombination current will it be comparable to that at any bias. We have just now calculated, it is here. This is 10 to the power minus 9, this is 10 to the power minus 11, and this quantity in the forward bias is increasing as e to the power of v by 2 v t. This is n is equal to 1, and if n is equal to 2, see, JGR is going up as JGR naught into e to the power of 2 v t minus 1, of course. I can always neglect that the moment you go to 50 millivolts, 100 millivolts forward bias. So, where will I put this curve? Supposing this is drawn like that, that means n is equal to 1. N is equal to 2 would mean it does not, it increases slower like that. This is n is equal to 2, or okay, let me put it as n is equal to 1, okay, 50 millivolts per decade change in current, and this one will be 120 millivolts per decade. 120 millivolts per decade. So, that is that quantity. Why I plotted this is, you have found out that this value is smaller and it remains smaller right through, it is not changing that current. So, the conclusion is, in the gallium arsenide based devices particularly, you do not have to worry about JGR or the Schottky barrier diode. All the time it is smaller. Even in reverse bias case, unless you go to very large reverse bias voltages, it is not showing up at all. That is the conclusion from that. The generation recombination current in Schottky barrier diode is small, particularly in gallium arsenide. Okay, if you go to some other material which is it may become comparable under reverse bias conditions compared to thermionic emission current at room temperature. Okay. Let us just go to next. This is the one which is talked of very much, and it is affecting the IV characteristic quite a bit. The main cause for non-ideality is this one, which is not there in the case of p-n junction. Okay. This is effect of image force lowering. Okay. If you look back always, so I do not want to look back now. Okay. there is a projection here. If I have a mirror there, the projection of that seen on the other side, exactly the same distance behind. Okay. So, if I have a metal like this, and if an electron is coming near that, it induces positive charges on the metal. The effect of the positive charge, it is a distributed charge all over the metal. If minus q is there, plus q is there. Now, you can examine or you can analyze the effect of the plus charge, distributed charge, by considering that there is no charge here, but an image of that on that side. That is the image. Is the electromagnetic theory, those who have learned, you will know that image charge effect, minus charge here, plus charge there. So, you do not have to consider the charge here. Okay. What we are trying to point out is, when the negative charge is here, because of the induced positive charge there will be force of attraction between the two. There will be force, this metal will not move, the charge experiences a force, attractive force in that direction. To compute that force, an artificial thing, that is image charge plus charge can be put on the back side and compute the force. That is called image force. Okay. Strictly, there is no charge there, there is nobody there. Okay. It is only the image, the effect of that you are seeing. So, the charge is actually here plus charge. To compute that, you assume that there is a charge on the other side. So, you can see electrons close to the conducting metal plane induce a positive charge on the metal surface. Okay. And this can be taken into account by considering a image charge. I will just put that diagram. Okay. Whatever I have been telling, now put in the diagram. This is the metal surface, that is that one charge I have put there. Now, it induces positive charge here, but then it is a distributed charge. The whole effect analysis becomes very complicated. Okay. But instead of considering a positive charge here, you put a plus charge here exactly at minus x distance, same distance. So, this is the image charge of this electron. So, you can compute the force induced, force due to the induced charge here by putting this image charge. What is the effect of that? Okay. So, that means there is an additional field coming up. When you take a look at the energy band diagram in thermal equilibrium or under forward bias conditions, what you plot there is due to the built in potential, due to applied voltage, etc. What we are talking of is apart from that. Okay. Due to the image charge, there is additional force comes up. I do not have to explain this particular term. Coulomb's law of force, Q1 Q2 divided by 4 pi epsilon, distance is 2x square. So, minus q squared by 16 pi epsilon x squared, that is the force that this electron experiences, and it is pushing it in that direction. Okay. So, that is what he said. An electrostatic force is produced as if there were an equal positive charge located at the mirror image of the body in the plane. And I say is of the body, I am sorry, this is a body, a mirror image is formed in the body of the metal. That is what we say there. Okay. Now, let us go further down. So, with that, once you know the force, you can estimate energy, potential, etc. of the electron. What we compute is the electronic potential, which is same as the energy band diagram. Okay. Electrostatic potential is opposite of electronic potential. So, now force you know, and the energy is integral of the force. Force into distance is the work done, energy. Okay. That is the energy when the electron is brought from infinity to that point. All through it is experiencing the force of its own image. That is a funny thing. Its own image is forcing it towards, pushing it towards this metal. So, that force and that energy that is acquired by that, because of that, that is actually this one, integral of that. The square goes off, okay, and you get that. Now, potential of the image. In fact, electronic potential is, you remove that one q from there, energy is q into V. I am just finding the electronic potential, which is the same variation as the energy band diagram. When you see the plot, it will become clearer. So, I remove that q there, becomes potential. Energy is q into V, I remove the q, it becomes potential. That is what happened there. Okay? And minus sign is there. Let us go to the next diagram and see. This is the plot of that potential. Okay? This is the plot of the potential. What is the electrostatic potential? Go back to the diagram. That is plus, that is minus. Electrostatic potential is increasing in that direction. Okay? That means electronic potential, which is negative of that, is decreasing. So, that is actually what is told in this equation also. Electronic potential is minus there. So, as x becomes smaller, it becomes larger. At x is infinity, the potential of the electron is 0. That is what is put here. Potential is 0 there, I am just putting, if the 0 level is put and shifted down, you will get that. Okay. The variation of potential, nothing there, starts falling as 1 by x, goes down. This is due to the image charge. I call it a psi image. Okay. Slightly involved concept, but it is not difficult. All that you have to understand is, apart from the usual energy band diagram or the potential, you got one more term it has to be considered, that is that. Okay. Now, if you look at this particular diagram here, that is actually the energy band diagram which you usually see. Okay. And that can be obtained like this. That is due to the electric field. Okay, let us just see that. I think I must draw the diagram here. That is the metal, that is the N semiconductor, and that is the depletion layer. Okay. I just draw it slightly below, so that you are clearly able to see it. Okay. Depletion layer, which has plus charge, and there are negative charges here. How is the electric field coming up? I am just showing whether bias is there or not bias there. Electric field, this is actually the external field, which is coming up not due to the charge. You call it as, in fact, the charge is the external one, but this is the one which is present due to depletion layer. That electric field is negative. That is the E external, which is actually field due to the depletion layer. I am just calling still as E external because this is a term people have been using in literature. I do not want to deviate from that. Okay. So, you have the electric field like this, and this is the E peak, that is electric field x. Okay. That is 0 to E peak, this field is 0 here. Now, you integrate that, and this is actually this particular field, what you have plotted there is linear. If I want to find out what is the potential here, that potential in thermal equilibrium is built-in potential. When I apply forward voltage, it is V B I minus V. When I apply reverse voltage, that is V B I plus V R. So, that is all what this is. We have been discussing this so often, now it is this. I am reiterating what we have been telling. So, now E external is, in fact, this is E external peak, the peak value. Okay. So, what we are plotting there peak value into 1 minus x by W d, where W d is actually the depletion layer width. This is W d. Okay. This is a standard equation for the electric field, peak value into that, and potential due to that is integral of that, and I am putting that minus sign to tell you that if you go this side, electrostatic potential goes up as x increases, but when you go towards that side, electronic potential decreases. Okay? That is how you draw the energy band diagram. So, that is why I put that minus sign there. Okay? Otherwise, when you integrate, if you are putting electrostatic potential, you will put integral of that will be minus sign will go, because minus E peak into that. So, anyway, we can very easily understand from physical terms that from the x equals 0 right side when you go, electrostatic potential becomes more and more positive, electronic potential will become negative, just opposite. Okay. Now, just let us plot that. So, this one more thing that I wanted to show you here is this term, when you are talking of x very, very small, that term will be negligible. What I am trying to point out is, you integrate this, okay, you get this particular term, or you do not have to worry about the whole thing at all. Compared 1, x by W d will be small. When you integrate that, you get first term alone. You can delete this term completely. You can say E peak into 1 minus x by W d. I can put it as E peak, okay, a constant term up to some bit. It is like this. This particular current portion, if I take only a small portion, that variation I do not consider. It is almost a constant. That is the meaning of that. So, in that small region, if I plot, that will be like that. I am just putting it because people want to talk in terms of peak value, and also what matters is what happens around that peak value. Okay. Now, let us take a look at this. So, the plot here, see here that E peak into x is there, it is linear there, but as you move away it deviates from linearity, which actually contains the whole integral, complete integral. If you take this is the one. I hope there is no confusion here. What we are plotting here is the electronic potential, which actually is the energy band diagram which we have been plotting all through. Okay. This is the energy band diagram which we have been plotting all through. That is the electronic potential, that is the psi external. Now, this quantity here on the other side is the additional potential that comes up. Okay. So, what is the total potential? Okay. Let me just plot that here, because that diagram it may become. See, what we have is one potential varying like that, which actually is the energy band diagram itself. What we are talking of linear, it is only on this portion. You do not have to worry about the linear term. You can take the full term, integrate it, you get it like this. Okay. Now, the second term is, this is actually the psi external, we call it. Now, the image force term that we have been talking, that comes from like this. As we come closer and closer, 1 by x, it becomes more and more negative. Actually, when x equal to 0, that goes down to minus infinity. Okay, but we are just putting it just close to that point. So, what is the sum of these two? This is psi image force or image. So, total potential variation or the total band diagram variation will be sum of the two, and sum of the two will be, here it is very large compared to that. So, it follows that you add this quantity, these two quantities, it comes like this, and beyond that point, that is 0, that is not varying. So, entire variation comes up now like this. That is what I plotted there. Okay. So, variation, total variation is like this. Supposing I take this as 0, it is not actually 0, it is I take a reference as 0. From that point onward it has come down by this quantity. How much has it come down? This is by how much it has come down. Usually what we take is, that is the phi bn we take. Okay, that is the phi bn. Now, the new band diagram is like this. I have exaggerated it tremendously. The new band diagram is like this. So, what was going earlier like this has become like this. So, what is the new barrier now? The entire reduction here is because this has pulled this down. The potential energy of the electrons has been pulled down in this portion because of the image force lowering effect. And the new barrier, this is without any image force lowering effect. Let us say put phi bn naught, that is absent. When you take that effect into account, this is actually the phi bn. And the reduction in the barrier height is this. This is delta phi bn. Okay. So, what we are telling is, I hope there is no confusion about the thing. We are redrawing the energy band diagram. The initial energy band diagram, it was due to the electric field integral and the potential is like that, depletion layer. Now, superimposed on that, you have got this particular another potential due to the image force, which is force integrated and potential put. So, actually the barrier gets reduced by this amount. Okay. So, how much is that barrier? The reduction in the barrier, delta phi bn. How do you find out that? Sum of, you add these two together, differentiate it with respect to x, equate it to 0, find out the new phi bn. That is all what we do there. So, when you do that, do not worry about the signs delta phi, I just used delta phi just to show that the reduction in the phi is that quantity, total sum of them. Okay. So, what we are talking of is the total potential now. This line here is the psi. Okay. Psi image, psi external, okay, and some of them is psi f x. Is it all right? So, maximum value you find out by taking this expression here, differentiate it, okay. I think we will just sum up today some of the things that we have been discussing, okay, because let me not get into this, because I will take it up in the next lecture once again this particular thing, okay, because I will just go back to this point here, from there onwards I will just discuss this once again, okay, because it will take some time for us to absorb the whole thing, the concept of that, because this is the one which affects your ideality factor. So, what you can see from here is the generation component does not affect, the whole injection does not affect, they are all small quantities, but image force lowering could affect, because from these two diagrams you have seen that the potential barrier, which was phi bn naught, gets reduced by an amount like this, because this is the only energy band diagram. So, the energy band diagram, instead of being like that, now turns out to be like this. I have exaggerated this. So, that is the reduction in the barrier. So, that is called the image force lowering effect on the barrier, and then that happens, the extent of current that is crossing will change. In fact, your J naught itself will change. See, how much is the lowering effect, that will affect your J naught. If more is the lowering, current will be more, the J naught will become more. Correspondingly, the forward current will change differently. Okay. Now, it affects differently in the forward and reverse directions. One pulls up, one pulls down this barrier. That aspect we will discuss in the next lecture, because I want to go back to this, bring back to the whole thing in details. Okay. See you next time.